Isometric projection is a way of showing a three-dimensional object on a flat sheet so that the three principal axes x, y, z appear equally inclined to the viewer. Imagine looking at a dice that is turned so you can see three faces at once. Each face is tilted the same amount. The key principles are: equal angle rule. The three axes are spaced 120 degrees apart in space, but when drawn on paper they are laid out as 30 degrees from the horizontal line on both sides, forming a 30-30-30 degree system. Foreshortening, because the axes are not perpendicular to the picture plane, any line drawn along an axis looks shorter than its real length. All three axes are shortened by the same factor, called the isometric scale factor, which is 1/2 times the square root of 2, approximately 0.707. This means a real length of 10 millimeters will appear as 7.07 millimeters on the drawing. No perspective, parallel lines in the object remain parallel in the drawing. There is no vanishing point. This makes measurements easy once you remember the scale factor. These principles let engineers quickly visualize dimensions and relationships without using complex perspective drawings. Explanation: to start any isometric drawing, you first create the three axes on your drafting sheet. Think of the axes like the edges of a 3D coordinate box that has been tipped over. 1. Draw a horizontal baseline. This will be the x-axis. 2. From any point on that line, draw two lines at 30 degrees above the baseline, one to the left and one to the right. These are the y and z axes. Use an adjustable triangle or a protractor to get the exact 30-degree angle. 3. Mark equal intervals on each axis, for example, 5 mm marks. Because of the foreshortening, the spacing you mark is already the reduced length. You do not need to multiply by the scale factor at this stage. 4. Connect the marks with light pencil lines to form a faint isometric grid. The grid consists of parallelograms whose sides follow the three axes. This grid acts like graph paper for isometric work. It guides you to place points accurately. 5. Secure the paper on a drafting board. Many textbooks recommend a light blue tracing paper so that the grid can be reused. The 30-degree, 30-degree, 30-degree system mimics the view you get when you look at a cube resting on a corner. Each visible edge is equally inclined. Basic geometric entities behave in predictable ways when projected isometrically. Lines, principal lines, those that run parallel to one of the three axes, are drawn exactly along that axis and automatically receive the foreshortening factor. Example: a wall that runs straight forward in a building plan becomes a line on the y-axis. Receding lines, those not parallel to any axis, are drawn by connecting corresponding points on the grid. They will appear at a 30-degree angle to the nearest axis. Circles, a true circle whose plane is parallel to one of the three axes becomes an ellipse. The major axis of the ellipse is the true diameter, no foreshortening, while the minor axis is shortened by the scale factor 1/2 times square root of 2. Imagine looking at a coin placed flat on a table. From an isometric view, the coin looks like an oval. Arcs, treated like parts of circles. You draw the underlying ellipse first, then trim the portion you need. Use a compass on the isometric grid to locate the center and then sketch the ellipse. Ellipses. If the original shape is already an ellipse in a plane parallel to an axis, each of its axes is foreshortened accordingly. For a general inclined ellipse, you must project several points around its perimeter onto the isometric axes and smooth the curve through them. Remember, any curve lying in a plane that is parallel to the picture plane, the paper, remains a true circle. Otherwise, it turns into an ellipse with the known foreshortening. Projecting simple solids follows a repeatable sequence of locating key points and then connecting them. Prism, for example, rectangular block. Locate the 8 corner points on the isometric grid using the axes and the actual dimensions multiplied by the scale factor, 1/2 root 2. For a 40 mm by 20 mm by 10 mm block, mark 40 mm along X, 20 mm along Y, and 10 mm along Z, each reduced to 28.3 mm, 14.1 mm, 7.1 mm on paper. Connect the points to form 3 visible faces. Hidden edges can be drawn with dashed lines. Cylinder axis parallel to an isometric axis. Draw the 2 ellipses for top and bottom faces using the major axis equals true diameter. Minor axis equals diameter times 1/2 root 2. Connect the corresponding ends of the ellipses with straight lines parallel to the axis. These are the side lines. If the cylinder's axis lies along x-axis, the ellipses are drawn on planes parallel to y-z. The side lines run at 30 degrees to the baseline. Cone apex on an axis, base parallel to a plane. Draw the base ellipse as for a cylinder. Locate the apex by moving along the chosen axis the foreshortened height. Connect the apex to the perimeter of the base ellipse with straight lines. These become the slant edges. These steps help you build up more complex shapes by stacking simple ones. Explanation: when several solids interact, treat each one separately first, then apply Boolean operations union, intersection, subtraction in the isometric view. The step-by-step method. Sketch individual solids on the same isometric grid using the rules above. Keep each solid in a different color or layer for clarity. Identify the region of interaction. For union, you simply keep all outer edges and erase interior lines. For intersection, keep only the overlapping portion. For subtraction, remove the volume of the second solid from the first. Project the common edges. Find the points where the solids intersect by solving simple geometry, for example where a cylinder cuts a block. Use the isometric scale factor to locate those points on the grid. Redraw the outline, erase hidden interior lines, replace them with the new outer boundary. Use dashed lines for edges that are hidden behind the remaining material. Add dimension lines, indicate the true dimensions of the resulting shape, remembering to apply the 1/2√2 factor for any measured length along an axis. Real-world analogy: think of building a Lego model. First you place each brick solid on the board, then you decide which bricks stick together union, which bricks carve out space inside other bricks subtraction, or where bricks overlap intersection. The final model shows only the surfaces you can see. Because every line drawn along an isometric axis is shortened, you must convert measured drawing lengths back to real dimensions using the scale factor k equals 1/2 times square root of 2, approximately 0.707. A procedure. 1. Measure the length on the drawing, L sub p. Use a ruler or the grid scale. 2. Compute the true length, L sub t, by dividing by the scale factor. L sub t equals L sub p divided by k, which equals L sub p divided by 0.707. Equivalently multiply by square root of 2, approximately 1.414, and then by 2. Example: a drawn edge measures 5 millimeters. The real edge is 5 divided by 0.707, approximately 7.07 millimeters. 3. For dimensions that are not parallel to any axis, for example a diagonal across a face, first resolve the diagonal into components along the axes, apply the scale factor to each component, then recombine using the Pythagorean theorem. Suppose a diagonal across a 30 mm by 40 mm face is needed. The projected components are 30 mm times k and 40 mm times k. The drawn diagonal length is the square root of open parenthesis 30k close parenthesis squared plus open parenthesis 40k close parenthesis squared, which equals k times the square root of 30 squared plus 40 squared, which equals k times 50. Measuring the drawn diagonal gives you 35.35 millimeters, because 0.707 times 50. To recover the true diagonal, divide by k, yielding the original 50 millimeters. This systematic use of the scale factor ensures that every dimension you read from an isometric drawing can be translated back to the object's actual size. Explanation: the isometric scale factor comes from the geometry of projecting a 3D axis onto a 2D plane. Derivation. 1. Imagine a right-hand coordinate system with unit vectors I, j, k along the x, y, z axes. 2. Rotate the system so that the three axes are equally inclined to the view direction. This is achieved by first rotating the object 45 degrees about the vertical axis, then tilting it 35.264 degrees, arctan of square root of 2/1 about a horizontal axis. After these rotations, the direction cosines of each axis with respect to the picture plane become identical. L equals m equals n equals 1/square root of 3. 3. The projected length of a unit vector onto the picture plane is the magnitude of its component in the plane, which equals square root of L squared plus m squared for any axis. Substituting L equals m equals 1/square root of 3 gives. Foreshortening factor equals square root of 1/square root of 3 squared, plus 1 over square root of 3 squared equals square root of 2 over 3 equals square root of 2 over square root of 3. 4. However, conventionally engineers scale the drawing so that the grid spacing is equal on all axes. Multiplying by a constant to make the grid spacing convenient leads to the factor k equals 1/2 times square root of 2. Proof: let the true unit length be 1. Its projected length on the paper is square root of 2 over 3. If we choose a drawing unit of d such that d equals square root of 3 over 2, so that 3 drawing units line up with the true unit along an axis, then the projected length becomes d times square root of 2 over 3 equals square root of 3 over 2 times square root of 2 over square root of 3 equals square root of 2 over 2 equals 1/2 times square root of 2. Thus, every line parallel to an axis appears shortened by 1/2 times square root of 2 relative to its true length. This derivation explains why the same factor works for all 3 axes and why it is built into the standard isometric grid. Even experienced students slip on isometric drawings. The most common pitfalls are incorrect axis angle, drawing the axes at 45 degrees or 60 degrees instead of the required 30 degrees leads to wrong foreshortening. Always check with a protractor. Forgetting the scale factor, measuring directly from the drawing without dividing by 1/2 root 2 produces dimensions that are about 30% too small. Mixing true circles with ellipses, a circle whose plane is parallel to the picture plane should stay a circle. Drawing it as an ellipse causes errors in later calculations. Hidden line errors, forgetting to dash lines that are obscured makes the part look solid and can hide important features. Over-projecting combined solids, when subtracting one solid from another, students sometimes keep interior edges that should disappear. The rule is after the Boolean operation, erase any line that lies completely inside the remaining volume. Dimension placement, writing dimensions along the projected axes without correcting for scale, makes the dimension label itself misleading. How to avoid them? Use a pre-drawn isometric grid as a template. It forces the 30 degrees angles. Keep a small cheat sheet with the factor 0.707 or 1/2 root 2 handy. After finishing the outline, walk through a checklist: axes correct, circles correctly rendered, hidden lines dashed, dimensions scaled. Practice a few error spotting exercises where you are given a flawed isometric and asked to locate mistakes. By internalizing this checklist, exam performance improves dramatically. Problem 1: Fundamentals in scale factor. A steel rod of true length 120 mm is drawn in an isometric view along the y-axis. The measured length on the drawing is 85 mm. Determine the scale factor used and verify if the drawing follows the standard isometric factor. Solution outline. Standard factor k equals 1/2 square root of 2, approximately 0.707. Expected drawn length equals 120 mm times k equals 84.84 mm, approximately 85 mm. Hence, the drawing uses the standard factor. Problem 2: Combined solids union. A rectangular block 80 mm times 40 mm times 30 mm, length times width times height, has a cylindrical hole of diameter 20 mm drilled through its height, centered on the top face. Produce the isometric view of the resulting solid and label the true dimensions. Solution outline. 1. Sketch the block using the isometric grid. Mark the 3 visible faces. 2. Determine the center of the top face. Move half the length 40 mm along X and half the width 20 mm along Y. Apply K to locate on paper. 3. Draw the hole as an ellipse on the top face. Major axis equals 20 mm, minor axis equals 20 mm times K. 4. Extend the ellipse vertically by the height, 30 mm times K, to represent the side of the cylinder. Use dashed lines for hidden portions. 5. Erase interior lines of the block that are now removed by the hole. Keep only outer edges. 6. Add dimension lines. Block dimensions on visible edges, hole diameter labeled on the ellipse, all values expressed as true dimensions. Problem 3: Intersection and true lengths. 2 right circular cones intersect such that the apex of cone A, height 60 mm, base radius 30 mm, lies on the base circle of cone B, height 80 mm, base radius 40 mm. The axes of the cones are perpendicular. Sketch the isometric view of the intersected volume and compute the true length of the line of intersection as seen in the drawing. Solution outline. 1. Choose axes. Let cone A's axis align with X, cone B's axis with Y perpendicular. 2. Project each cone separately using ellipses for bases and straight lines for sides, applying K for all dimensions. 3. Locate the apex of cone A on the base circle of cone B. Find the point on the y-axis where the distance from the center equals 40 mm, radius of B use components. X-coordinate equals 0, y-coordinate equals 40 mm times k, z-coordinate equals 0. 4. The line of intersection is the curve where the two surfaces meet. For this simple case, we approximate it by the straight segment joining the apex of A to the point on B where the two axes cross. The center of B, its true length equals square root of open parenthesis 60 squared plus 80 squared close parenthesis equals 100 mm. 5. In the drawing, the projected length equals 100 mm times k equals 70.7 mm. Measure that on the sketch to verify.